Okay, so let's try to deal with the 2-3-1 neural network architecture. So 2 nodes here, 3 nodes here, and 1 node here. And we have a set of weights here. Each one of these is connected to each one of these. So that means there's going to be 6 weights there. And then we also have here, each one of these is connected to this one. So that's another 3. And the notation here, we've already talked about this kind of notation. And here we'll call this W2, W2, W2. And this is W2, 1, 1, 2, 1, and 3, 1. And this is just a kind of illustration of the dimensions of the vectors, or the matrices that are involved. So here we're going to have a 1 by 2. As opposed to a 2 by 1 maybe. And then here we're going to have a 2 by 3. And here, this one we're going to represent, say, this one or this one as a 1 by 3. And these 3 weights here can be represented as will be represented as a 3 by 1. And then here, this is represented by 1 by 1, or just a scalar output, but we could call it a 1 by 1 matrix. So here we have a 1 by 2 and a 2 by 3, and we're going to do matrix multiplication, and that's going to give us the 1 by 3 here that we expected. And here, from the picture, you can guess that probably this is going to be a 1 by 3, and this is going to be a 3 by 1, and if we multiply them, we'll get a 1 by 1. So the picture suggests the operations that we're going to perform. So first we will talk about coding the feed-forward process. So that means how the data gets transferred from here out to here, or maybe even through to J. And then we're also, of course, going to code the back propagation process as well. So that occurs here, and we'll need the derivatives for W2 and the derivatives for W1. And again, we see that W1 is a 2 by 3, and if you want to see just how we express it, here it is 2 by 3. We've seen that before. And we also have the W2 matrix, which is a 3 by 1. So we just want to write the code that will push the data from here out to here, and then also to J. And we're going to allow for a little bit of flexibility, so we're going to create variables called input layer size, hidden layer size, and output layer size. And we're going to set them to 2, 3, 1. Input layer size is 2. This layer size is 3. What did I call that? Hidden layer size. And this one is 1. But we can change that, and we can then create a different structure and we can test different structures. In particular, we can change the layer size and get more nodes in the hidden layer. Or if we want to have more inputs over here, we can also change that. So we'll create these variables and start them out as 2, 3, 1. And since writing subscripts and so on is quite difficult in R, I don't know how to do it, we're just going to write W1 sub 2, 3 to mean this weight here, W1 sub 2, 3. Now, we can also take that matrix if we call it capital W1 like this. So if this matrix is called capital W1 here, if we define a matrix like that, then what does this refer to? This refers to the element in the second row, third column. So this is exactly the, this refer to the same thing. So this is like a name for it, but this is a way to access it from within the actual matrix. So we can, if we bother to define this, then of course we can use that. But if we've already defined this, then we can always use this method of accessing the particular weights. Now, here's something that I forgot to mention in previous videos, but as mentioned earlier in the text, note that other texts may use the reverse indexing for the weights of the network diagram. So if you start to read some other text, just don't get confused. They may be, instead of calling this one W23, they may call it W32. So they may reverse the indices. So W32 in their terminology would be the weight which that goes from here to here, the same weight, but they may reverse the indexing. So in this text, we're using 2, 3 to say that it starts at 2 and originates and ends at 3. That seems like kind of very natural way to identify the indices. Say that first index tells you where you're coming from, and the second. But there are sometimes convenient reasons to have it switched. So another book might have it completely opposite. So hopefully you won't run into that, or at least if you do, you'll know that that's what they mean. So you won't be completely confused. So here we have here we're creating as we did earlier, this is a vector with consisting of the two inputs, x1 and x2. Notice this is a capital X here. And then if we want to, we can convert that vector into a matrix. And here we're saying with just one row, and the input layer size is the number of columns. So we had set input layer size to 2, so this would be a 1 by 2, which would work just fine for this. Now we want to create a matrix, and we want to assign the values randomly. We said we were going to initially assign the weights in the weight matrix to random values, and we're going to do it between -1 and 1, and then pass that into the matrix functions. We're going to create a matrix where we set the number of rows to the input layer size and the number of columns to the hidden layer size. So just going back here, the input layer size by 2 by 3, which is exactly what we want, a 2 by 3 matrix. And so that 2 by 3 come actually from the input layer size and the hidden layer size. If we had, for example, the hidden layer size was 4, then what matrix would we want? Let's think about it. So instead of this, if we had the hidden layer size was 4, you can sort of see that we'd want one more column here because we have 3 columns because there were 3. There are other ways to confirm this, but this is kind of a not very deep way to confirm it. But you can see that we have 1, 2, 3, so probably we'd want one more. There are other ways to think about it. We're probably a little bit deeper. But anyway, we would want a 2 by 4 if we had 4 nodes here. So you can check that. You can think about that yourself just to confirm it. You can see, for example, that if this was 1 by 2 and this was 2 by 4, then we would get a 1 by 4 out. So that also suggests that we need a 2 by 4. And then you could just check that we're actually getting the right calculations as well. So this one times this one, we saw it does give you this one. This one times this one does give you this one. This one times this one does give you this one. And so, of course, if we had one more column here, this one times that last column would give us what we need for the next node. So that's a kind of argument for why the size of the matrix is going to be the size of the number of inputs, or the input layer. I guess it would be here the what did we call it? Well, anyway, the input layer size times the hidden layer size. So now going back to this, we need to create such a matrix, and we want the weights to be random size. So let's see how we do that. Sorry, we want the weights to be random values between -1 and 1. So instead of using this was just an example, where we would, we had, oh, I'm sorry, no, this is right for the X matrix, given that these are the values of the X's. But for this matrix, we're going to set random values. So we want to put in, we want to create a matrix. We're going to use the random number generator, RUNIF, which means random numbers selected from a uniform distribution. So I'm not going to talk about what is meant by uniform distribution, but you can look it up. It's very simple. We'll just say anyway that they're random numbers, and the we have, let's see, one comma here, another comma here. So there's 3 entries that go into the random number generator. And the first entry is, in this case, the input layer size times the hidden layer size. So that was 2 by 3. So that's going to, the first entry here is 6. So that's the number of random numbers we want to generate. Then then there's a comma, and then after that, the minimum size of the random number is -1, and the maximum size is 1. So we want to generate 6 random numbers between -1 and 1. That's what this does. And then we're going to put that into a matrix. And here's the matrix function's first bracket. And then there's another comma, there's a comma and another comma. So that means the first entry in the matrix function is the values. Basically, this gives us this is like a vector here, just like this was a vector. We put a vector in here. Here we're also going to put a vector into this matrix function, but this vector is going to contain these 6 random numbers, because that's where the comma that's where the first comma is. And then we have to say the row size and the column size, and the row size is the input layer size 2, the hidden layer size is 3, at least as we defined it up above. So we'll have created a matrix like this with random numbers for each of these entries. So that's the way we want to start out. Then we said that to get the Z1, Z2, Z3, that is to get this, what are we going to do? We're going to take this matrix times this matrix, and that's going to give us the correct values for the Z entries. So we want to define Z3, I guess, no, sorry, Z2, 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 Z2. So we're going to call this matrix Z2. It also, we also have A2. A2 is the next step, where we put this into the sigmoid function or into the threshold function. But anyway, Z2 comes from this times this. So that's what we have in our code. So we say that Z2 is X times W1, and this is the matrix multiplication. So that's exactly what we want for Z2. And we can check, we can print out Z2, and we see that we get a 1 by 3 matrix. We could say Z2 is supposed to hold the 3 input values of the 3 nodes in the hidden layer. Of course, it could be more. We said we could change the number of nodes. We can see from the fact that that Z2 equals this, that the number of columns of W1 is also the same as the number of nodes in Z2. Okay, for example, we can write Z2 sub 1, and that could also be written like this, Z2 1 1. And that should contain X1 times W1 sub 1 1 plus X2 W1 sub 2 1. So we've done this many times already, and we're just writing it this way, but we've covered this concept many times already. So that's what Z2 sub 1 should equal. This is Z2 sub 1. This is Z2 sub 2. This is Z2 sub 3. So, and how we of course we know how to get this, and this formula gives us the calculation. And if you just want to do a check to see that this is all really true, of course we know it is true. It's not that mysterious, but if we want to know, well, what is Z2, the first element of Z2? And we hope that it's the X11 element times the W111 element plus the X12 element times the W21 element. And so we can check to see if that's true or not, and it is true. You can also check it a different way. You can check it this way, so I'll let you read through this in the text, but it's just another check that you could do if you want to, just to make sure that we're on the right track. But we expect that we are. Okay, next we want to talk about how to get to A2. So we get the Z's here, and then we get the A's, and the way, of course, that we get the A's is to pass this element into the sigmoid function. So next, the sigmoid function is applied to each of the values of Z2 individually to obtain A2. And actually, though, in R, not so much in other languages, but R is perfectly suited for this operation because when you take a function and apply it to a vector or to a matrix, R actually applies the function f element by element to the vector, which is exactly what we want here. So that's convenient that R does that. So we don't have to do it element by element. We can just take the whole Z2 vector or matrix, and in this case, I guess it's a matrix, Z2, and we can just put that into the sigmoid function, our sigmoid function that we built. And by the way, I didn't mention that, but up at the beginning, we said we're going to need these two functions. I'll just go back there. So this is at the beginning of the feed-forward discussion, and I said we'll need both of these functions, sigmoid and sigmoid prime. So we define them here so that we can use them down below. So we use them right here. Sigmoid of Z2 is A2. Now we can see that A2 is still a 1 by 3, and hopefully these are correct. Of course they are correct. We're just passing Z2 into sigmoid. So that is handled very nicely by R, very simply. We just do this, and we get the entire transformation of the entire matrix element by element. So to recap, so far for A2, or so far in the feed-forward process, we have A2 is sigmoid of Z2, but Z2 is this, so we could say sigmoid of this. So far, a single matrix equation represents the entire process, so that's nice. Not necessary to do it this way, but it certainly is nice to be able to do it this way. Okay, so now we have to move on from, we have A2, and next we want to take the matrix, we're calling it W2 here, and we have to do something with A2. So we have A2, these values here, and of course what we want to do with these weights is multiply the first element of A2 by this weight, the second element of A2 by this weight, and the third element of A2 by this weight. So let's work on that. So first of all, we have this weight matrix. We've talked about it here. Or actually we haven't talked about it. It's right below here. So this is the weight matrix W2, and we're going to have to create it in a similar way. That is, we want to assign each of these randomly, random values between -1 and 1. We're using the same kind of thing here, but this is not going to give us 6 entries. It's the hidden layer size times the output layer size. This is 3 times 1. It's only going to give us 3 values. That's all we want, is 3 values. So that's good. And then we're going to make a matrix out of it, and it's going to have the dimensions of hidden layer size by output layer size. And the hidden layer size is 3, and the output layer size is 1. So it's going to have dimensions 3 by 1, which is what this mathematical expression has, 3 by 1. So just reading up here, A2 is a 1 by 3 matrix. That was A2, and then W2 should contain the weights between layers 2 and 3. So we just saw that picture. That's what this is. The dimensions may be 3 by 1 or 1 by 3, because we need 3 of them. So why do we say that it has to be 3 by 1 instead of 1 by 3? So if W2 were designed to be 1 by 3, this calculation A2 times W2, or A2 is 1 by 3, and if this was 1 by 3, we couldn't do that. Couldn't do this matrix multiplication. Note that it is possible to consider reversing the factor. So if we did W2 times A2, so put the W2 over here and the A2 over here, then we would have what? W2 would be 1 by 3, and A2 would be a 1 by... no, that wouldn't work either, would it? Okay, that may be an error. But anyway, we're not doing that, so it doesn't matter. So I mentioned that we're trying to have a convention that we always put A2 to the left of W2 because we have a convention that says left-hand factors should be upstream of right-hand factors. So this, so here we have A2 is upstream of W2. So we're trying to stick to that here so that we wouldn't write W2 times A2 besides the reason that it just doesn't work in terms of the dimensions, but also because we want to put something upstream to the left of something downstream. And again, note that other texts may not do this. So you could get confused. So you need to confirm in another text, if you're reading it, what kind of conventions they're using here. Now here we see that Z3 in this is a matrix, but we may convert it. In fact, here we are going to convert it to a vector. So that's not necessary, but just doing that. And again, it's definitely not necessary. Now we have Z3, and then we want to pass Z3 through the sigmoid function. Let's make sure. So now we have Z3, but how do we need to get this? And this is just passing this through the sigmoid function, so we need to do that next. So we do that here, and we call it y hat. We could call it A3, or we could call it y hat. Doesn't matter what we're going to call it, but we're calling it y hat here. And so then we can, once we have y hat, we can also talk about the cost j. But of course, to do cost, you need to know so y hat is the predicted value. You need to know the true value. So I said, okay, let's just pretend that the true value is 0.5. Then we can calculate y minus y hat and get some kind of error. So if this was the true value, then this would be the error. Now the feed-forward process of the entire 2x3 network can be represented by a single matrix equation. So let's see that. So here it is. It's just, we can say J, we're checking to see if this is true, and it is true, is 0.5, of course. Y minus, notice that we have just the original information here. We don't have like Z2, Z1, and so on. We just have X, the weight matrix at layer 1, the weight matrix at layer 2. We do all the calculations, and basically J can be expressed as a single matrix equation. So we have represented the entire feed-forward process. That's just this one equation. Okay, so next we need to do the backpropagation, and that's where we're going to need the derivatives. Just as before, backpropagation depends on the derivative of J with respect to all of the weights, so that we know how to adjust all of the weights. We're going to need the derivative of J with respect to this weight. This is in the second set of weights, right? This is W2. we're going to need the derivative of j with respect to this weight, the derivative with respect to this weight, and then also for all these weights also. So we need the derivative for each one of these, because that's how we're going to change each one of these, by using, just as we did before, the updating formula depends on the derivative of j with respect to each one of these. So that's what we have to work on now, the derivative. So we'll work first on the weights in W2, and then on the weights of W1. So in W2 there are 3 weights, and so there should be 3 derivatives: dj dw2 sub 1, dj dw2 sub 2, dj dw2 sub 3. We need to know all of those. Now I mentioned here that here I'm only talking about one subscript, sub 1, sub 2, sub 3. Maybe it's better to say, here I have dj dw2 sub 1, but maybe it's better to say dj dw2 sub 1, 1. So we should mention that it comes from the first row and the first column, but in this case of W2 there is only one column, so we sort of don't need this extra 1 there. So, but generally we would, generally we would need that. The only reason we only have one column in this particular case, the only reason we only have one column here is because here we only have one node. So if we had 2 nodes here, we would need 2 columns here. Obviously, we would need more weights here, and they would need to be in a second column. If we had 3 nodes here, they would need to be in a third column. So you can confirm that yourself. So again, we said that we want the partial of j with respect to W1, partial of j with respect to W2, the partial of j with respect to W3. And then once we calculate those, we could just put them into a matrix. We could just store them in a matrix. Why not? Nothing special about storing them in a matrix, but we could just put them here and give that matrix the name partial of j with respect to capital W2. Capital, so this is sort of telling us that it's a matrix, and it just contains these elements. It's just a place to store them. Okay, so there's a note here that says these are partial derivatives, but we're not going to use some kind of partial derivative notation in our R code. And also this is for W2, but the same thing is going to be true for W1. So to figure out dj dw2 sub 1, so that's here. This is W2 sub 1. Here I'm writing it 1, 1, but we said we're only going to write it as sub 1 in the R code here. So we're talking about this weight here. So you should see that if we have, imagine we have the j circle out here, and we're doing dj of that dw2 sub 1 or 1, 1, then really it's just like we only had one weight instead of 3 here, and we only had one node here, and we're just following out to that node. So the derivative will basically be the same thing as we had in either the 1, 1, 1 network or in the 2, 1, 1 network. So let's just go back and check what that was for the weight at this level, the W sub 2 level. So here it is, and this was just for W sub 2, but really we can just think of, we're talking about W sub 2, I'm sorry, W2, it was just W2 here, and we're actually talking about W21. I can just think of it as though it was just following the path, the same path that this is. So to get from W2 to J, we have to follow the same path in the 1, 1, 1 network, or this might be the 2, 1, 1 network, but in either case, to get from W2 to J is the same path as in the current network, the 2, 3, 1 network, getting from W2 1, 1 to j. It's the same path. So the derivative is going to be exactly the same. And so this is delta 3. But here is delta 3, so we could say it's going to be minus the quantity y minus y hat f prime of u, that's the delta 3, then times a2. So let's split the screen here. So it should be basically the same thing here. This one is dj dw2 sub 1 is y minus y hat. There's a minus sign, but here the minus sign is over here. And then f is sigmoid, so sigmoid prime, because we have f prime there, of u, or z3 actually is what it is. And then times a2 here, and here it's a21 because it's going to be the input at, well, let's just take a look at that. Before we only had one node here. Now we have 3, so it's not going to be that one node. It's going to be this node because it's connected to this weight. So it's going to be 8, 2, 1, but that can be written, we've said that A2 is a matrix, and this will pull out the first element of that matrix. So this is the same as what we had up here, and that's what it should be. So now we have this first derivative. So we have the first entry in here. We just calculated this one. And given the current values of all this stuff, we could actually print this out, and this is what we happen to get. Now remember, what is this really going to tell us? This is going to tell us how to adjust this weight. So we want to, and remember, we're going to subtract this from the weight to get the new weight. Let's ignore the learning rate for now. And so subtracting a negative means adding it. So whatever it is, that's the way that the algorithm is the gradient descent algorithm is telling us to adjust this weight to get a new weight. Now we have to do the same thing for this one and for this one, but the logic is still the same. It's just as though to get from here to j, it's just as though we had the 1-1-1 network, and we were going following j to here. Then there was only this one weight, and then going to this one node. So the pattern should be the same. So we want the derivative of j with respect to this weight, which we call w2 sub 2(1) or sub 2. In this notation, it's just w2 sub 2. And it's going to be the same thing as here. The only difference is going to be that the connecting node here is not A21, it's A22. So it's not going to be A21 here, it's going to be A22 here. And then, of course, for the last one, it's going to be the same thing again, but the connecting node on the left or upstream is A23. So except for that, the derivatives are the same. And we could also, again, define a delta to be everything to the left of this one. So that would be from here to here. And those are the same for this one, and for this one. We said the only difference is here, here, and here. So we could define delta 3 to be that part, which is what we have here. We can just see what it is, just for fun. And then we can call this delta 3 times A21, delta 3 times A22, delta 3 times A23. Now again, these are partial derivatives, but it's I don't know how to make a nice notation for partial, so I'm just using this for the derivative. But we can, now you can see that basically this is remember A2 is a matrix. We're just pulling out the first entry, the second entry, and the third entry. But we could just do this. We could just do A2 times this. Now, remember, this is a scalar, actually, right? Isn't delta 3 a scalar? You can see it's actually a scalar right here. You should also just recognize that from this calculation that it's going to be a scalar. There are no matrices in here, so it's just going to be a scalar, and it is a scalar. So this is we're taking the scalar, the delta 3 times this, scalar delta 3 times this. So if we want to make a matrix, now notice the notation here. This is capital W, and there's no sub here because we're talking about the whole W2, the whole, we're making this, which is partial of J with respect to W2. So it's a whole matrix, and it has these pieces, and we can just write it. Each one of these is basically the same, except for one has the first element of A2 in it, the second element of A2 in it, and the third element of A2 in it. So we can just, to write it here, we can just say, take A2, which is a matrix, right? This is a matrix, and scalar multiply it by this delta 3. So when you scalar multiply this times this matrix, of course you get a matrix, and that's just what we want here. We want a matrix, we want this matrix, and that's what we're getting. So now we can say that the matrix that we want is this. Now you might think, okay, well maybe it should be, maybe we want to take the transpose of this. Maybe that's the form that we want, because remember this is A2, I believe. No, I was wrong. A2 is a 1 by 3, but we could either take multiply by A2 like we were suggesting, or we could just take the transpose of this. We can still scalar multiply the transpose of this by a scalar, no problem. So we could do it either way. It's still going to contain the right information. It's just that, do we want it to be 1 by 3, or do we want it to be 3 by 1? So if we leave it just like this, then the derivative will be a 1 by 3. But if we do the transpose first and then multiply by delta 3, then this will be a 3 by 1. So we will choose 3 by 1 for reasons that will be clear later. But it doesn't matter exactly. We'd have to adjust other factors. But anyway, we're going to do the transpose. So now we can see what our matrix is. And here's what it is. So it has the 3 partial derivatives here. And those are the amounts that we're going to have to adjust. W2 sub 1, W2 sub 2, and W2 sub 3. Okay, so we got that derivative. We got dj dw2. That's half of the battle. The rest of the battle is to get dj dw1. So we want the derivatives for w1. That is, we want dj dw1, the matrix that contains all these derivatives. So we want the derivative with respect to 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. So this is what we want for the first one. And that's the derivative of j with respect to this weight, w1, 1. And this matrix here is called capital W1, and we want the 1, 1 element of it. That's what this is. So we could say we want it with respect to this weight. And we can see what this is. That's not the derivative, that's just the weight itself. So this is the current value of the weight. And now, let's see. What is the path? So we want the derivative with respect to this of j. Remember, j is out here. So how do we get to j from here? So we go here, then we go here, and then we go here. So again, it's the same. It's as though there was only, it's as though we're just at the 1, 1, 1 derivative. It's as though we're just looking at the 1, 1, 1 network, and we're going from x1 through the 1 weight to the 1 node to the next weight to this node and then to j. So that we can think of it as that. There's no other path that we have to worry about. So we take the derivative with respect to j. We're just going to be following this path. So really it's going to be the same formula that we saw in the 1, 1, 1. The only difference is that we're going to have to, for this one, it's going to be for x1. For another one, it might be x2. That is the last part here. Where is it? So this is the long chain rule. And the last part here, dz2 dw1 sub 1, 1. So the derivative of this with respect to this is going to be x1, but in another case, it's going to be x2. So this last piece is the only thing that's going to be different. Well, sorry, that's not true. Some of these will pass through here and through here. So they won't be all the same, actually, even except for this last piece. There will be another piece which is different, or several other pieces which are different. So let's pay careful attention to what we're doing here, actually. So up to, well, when we go from J to here, and here, we defined delta 3. So that's always going to remain the same. So this part is delta 3, and here it's a little hard to read this. So let's go back and look at this original network architecture. And we had this result. This was, if we're going all the way deep into the, back down to here, the derivative of J with respect to W1, we had this result. And we had this delta 3 in there. And delta 3 was everything except for the last 3 terms. Well, here's another way to express this. And delta 3 is everything except for the last 3 terms. So delta 3 is basically all of this green stuff. So delta 3 takes us all the way down to this last term here, to this term here, the gold one here, dz3 dA2. So that's this term, the derivative of z3 with respect to A2. So if we're going here and we want to get to here, the way that we'll go is through here, 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 and then here. So this third layer is here, and this second layer node is here, is this one here. So whereas here we have dz3 dA2, now we have this node here instead of this node. So instead of dz3 dA2, which is what we do here, it's here. So it's going to be dz3 dA2 sub 1. So we're going to have to change that to sub 1 when we're doing this network. So let's just write that in here. So I just changed that to A2 sub 1 instead of just A2, because here it's A2 sub 1. That's the node that we're going to pass through. And then this is also going to be we're going to need to change that to A2 sub 1. So I changed that to A2 sub 1. And then instead of, here we have dA2 sub 1 dz2, that was for here, but now this is called z2 sub 1, so we have to change that to z2 sub 1. So I have to change this one just to z2 sub 1. And then here, this is z2, so I have to change that to z2 sub 1. And this was w sub 1, but this has to be w sub 1. This is w1, and this would be w1 sub 1. So we need to make those changes. So this has to be the same as this does, and then this has to be w1 sub 1. And other than that, everything is the same. So now, hopefully, we have all of the correct pieces in to go from here. Imagine there's a J here. We go through to here, to here, to here, and that should be what we want. And you can see that this last piece here is the derivative of z2, 1 with respect to w1, 1, or w1 sub 1, or w1 sub 1, 1, and that's going to give us this value, x1. So remember that all of the green was delta 3, and then we have this. this, and this. So let's copy this and put it down here so we can refer to it. So let's ask, what is this gold term here? So that's dz3, here's z3, dA1. dz3 dA1 is going to give us W21. So that's what we have here. So first we have the delta 3, so that's here. Then W2 sub 1. And the next term here is the black one, which is dA21, dA21, dz21. So this is the, how do we get from here to here? That's the sigmoid. So we're doing the derivative of this sigmoid function with respect to this. So that's sigmoid prime with respect of z2 sub 1. So that's the black part. And then we said this last piece is x1. So you should go back and make sure you fully understand this, but this is the derivative for dw1 sub 1, 1. By the way, here we need the double subscripts. We do need the double subscripts because we have we have a more complicated setup of weights here. Okay, so that's the answer for the first derivative. That's the answer for this one, but we have to do all of them. But what's going to be the difference between this one, say, and this one? What is this one? This would be called W21. So what's the difference? And by the way, where's that? W21 is here. So what's the difference between this one and this one, or this weight and this weight? Well, actually everything is the same. If you go here, 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 and out to J, go here, back out to J, here, or you go this way. The only difference is that here we're going to have x1, and here we're going to have x2 at the end. So for our first one, we had x1, but we should expect that when we do this 2, 1, we change this to a 2 and do that one, 2, 1, let's see, do we have that? Yeah, here, what's the only difference should be the last term. So let's make sure that that's true. This one and this one, they're the same except for the last term. So here, by the way, we're saying we said that we want x1, but one way to write x1 is the full X matrix and then the 1, 1 element. And then to get the new one, this one here, sub 2, 1, it's going to be the first row, second column. So remember, this is what is this? What's the form of this? What are the dimensions of this? What are the dimensions of our x vector? I guess it was a 1 by 2, and so we're going to pull out the first column and then the second column. Let's just make sure that it was a 1 by 2. Yes, it's a 1 by 2. X was a 1 by 2. And so we're going to either pull out x1 or x2. And that means we're either going to take the first element, which if we're thinking of this as a matrix, we could call it the first row, first column, and first row, second column element. So that's what we have. The only difference between this one and this one is this is going to take the first column element, and this is going to take the second column element of the X input matrix. And then we have to do all the other ones, and you should make sure that you agree that all of the other ones are also correct. Then we note that it's possible to express all 6 of these as some matrix equation using matrices for X, W2 weights, Z2, and of course this. It will turn out that the following expression will be what is needed. So we take the transpose of X, matrix multiply it. Now notice here that this is a constant, delta 3 is a scalar, so this is just scalar multiplication. That's what R will give us, and that's what we need here. And that's because each of these is scalar multiplied here by this scalar. And so now we're going to multiply that times the transpose of W2. So you should check that all these weights, that all these dimensions work out properly. But one more thing to notice here is that what is this? What is from here? Well, just let's say from this D to this bracket. What kind of thing is that? What kind of object is that? Well, W2 is a matrix, so the transpose is a matrix. So scalar multiplying a matrix times a scalar is also a matrix. So this whole thing here is a matrix. Now we're doing some kind of multiplication here, and then times what? This is also a matrix. So, but this is not, this is matrix multiplication here. This is not the same symbol as here. So this is matrix multiplication. We're not doing matrix multiplication here because they're not the same symbol. This is R's way, and we've seen it already, of doing element by element multiplication. So hopefully these two things on either side of this have the same dimensions. Otherwise, element by element multiplication doesn't make sense. So you should confirm in your own mind that the dimensions on the left side of this are the same as the dimensions on the right side of this. Now notice that notice this bracket here and this bracket here. So that means we're doing everything inside of those brackets first before we do this. So again, so you should confirm that everything, that what's from here to here, well, here, that is the same dimensions as this. Otherwise, this doesn't make sense. We couldn't really do element by element multiplication. So you should make sure that they are. Remember that we call it element by element multiplication, or we also call it Hadamard multiplication. So this will represent all of these equations, this one, this one, this one, this one, this one, and this one. And we can see that when we do all of this, we get a matrix like this, and this is supposed to be the derivative matrix that we're trying to calculate, and hopefully it is. And so these give us all the derivatives, that is, they give us all of these. So you should make sure that you agree with all of this. Make sure that there's no error here. If there is, let me know. But otherwise, we have the partials of J with respect to all the weights in the first level. And that's all we needed to have to do the gradient descent method of updating the weights. So we have them here, hopefully, and then we can use them. Here's some more confirmation of the dimensions and so on. So you can go through that, make sure that the dimensions are working. Here's what we just said, that if we scalar multiply this times this, we get a row matrix like this. That is, we get delta 3 times the first element of W, the W2 matrix, which is this one, and then times the second element, delta 3, same delta 3, and same delta 3 times this one. And we can test it out and see what they are. Now we examine the Hadamard product. Let's just go through this a little bit more. So of this one with this one. So again, we have to make sure that this and this are the same dimensions. So we want this, that's this one, which is here, times this one, sigma prime of Z2. So sigma prime of Z2 is a matrix, so we're taking sigma prime of each element of that matrix. So we're taking sigma prime of the first element of the matrix, sigma prime of the second element, and sigma prime of the third. So we do see that this is a 1 by 3, and this is also a 1 by 3. And so we can do the Hadamard multiplication here, and we get just this time, this times this one, and then this one times this one, and this one times this one, which is what we have here. So that's this part here, and then we have to multiply that times t of x, because we're talking about, we just did this part here, then we have to multiply that times t of x, but that is not Hadamard multiplication, that's matrix multiplication. Remember, so we can see t of x here is a 2 by 1, and then this other piece is a what? 1 by 3. So 2 by 1 and 1 by 3 works, and we get a 2 by 3. So 2 by 1 and 1 by 3, we get this. And then, is this really what we want? Is this, for example, equal to this, or equal to this? So let's just copy that and see if it is. So we want to see if this is the same as this. And you can see that it is. Here's x1, here's x1, basically x1. Here's delta 3, here's delta 3. Here's W21, here this is W21, and here's sigma prime of Z2 sub 1, and this is sigma prime of Z2 sub 1. So you can go through and make sure that all of these are correct, but they do seem to be correct. And so we have the mathematical expression for the derivative matrix for W1, capital W1, all the weights in the W1 level, and we have the code for it as well. And we put all of that code in, gave it the name here. And we can finally define it here. So we just do all of this, and that's all the work we did. And we just give it this name. Okay, and this is also another expression, the mathematical matrix expression for this. You should check that this is also correct. Now we can rewrite this just like we did before. Instead of that longer equation, we can define a delta 2. But here, notice this delta has a capital D in its name, which suggests, hopefully, that it's a matrix. And it's not just a constant. And also we can see that this is matrix multiplication. So we have to carefully define this delta matrix if we want to bother to do that. We did do it before. In the simpler cases, we defined a delta 2. And here we can define delta 2 like this. And in the R code, it will be like this. And again, hopefully this is a matrix. We are using capital D here. And if we check it out, it is a matrix. You can see it's a 1 by 3 matrix. The dimensions are 1 by 3. And x, the dimensions are 1 by 2. So if we take the transpose of x times this, we get this as our delta 2 matrix. And if we do this, we can see that we get the same result. Here's the we're doing a test here, we can see that we get the same result as we did for this because all of these are true. So this is another way to rewrite this using this delta 2 matrix. Okay, so anyway, now we have expressions for this one and this one. And now we can update the weights for our 2 by 3 by 1 network. Now we can update the weights for all of these, and we have matrix equations to do it in R. And here they are. Here are the matrix equations. So we take the matrix with the W2 values. Remember, that's currently a, what's it? It's either a 3 by 1 or a 1 by 3. And then we're subtracting this from it. This is also of the same dimensions as this, hopefully. And then this one is a 2 by 3. And hopefully this is of the same dimensions, and we are doing, and we're subtracting that. We're actually multiple of those. So now we have this is the main thing that we needed to get, and now we can construct an update weights function and use these to update the weights. And when we do that, we'll get, we can make predictions given, and we can check the costs as well. Then we want to finally run an entire data set through the network. We're going to use a different data set this time. We're going to have something called, one input is going to be called calories burnt, and the other is hours of sleep. And the variable that we're trying to predict is mood. And we actually have, you can see there are two different colored dots here, and they stand for something else I can't remember right now. But anyway, we're going to try to, so this is people at the gym, so they do some exercise, and we also know how many hours of sleep they had, and then we have their mood. We have a way to measure their mood. Now, one thing that's kind of unfortunate about this data set is that there are only 3 different levels for the mood. So you can see like all the dots are up here, here, or here. So we are trying to, so there's only 3 possible values, 100 for the mood, 200, or 300. And one more thing. Okay, now this picture, and the code is provided so you can generate this picture yourself. But this picture, we're trying to fit a plane through this data. So that would be a regression line or a regression plane problem, or they sometimes call it a hyperplane. But anyway, in this case, it's just a plane is good enough. We're trying to fit a plane through this data. And you can see that you're not going to get a great fit here. You're not going to get all of the dots to fall anywhere close to a particular plane. So trying to do this with linear regression, or this can still be called linear regression even if you have a plane. So trying to do that problem is probably not going to give us great results. However, maybe our code, our neural network, might give us good results. So you do get the code for that picture if you want to generate it yourself. And this is using a package called Plotly. And then we also use something called Reshape. But basically Plotly will give you many great graphs actually. And then a little bit below the plot, we can do, actually this will give us, this is a way in R to do linear regression. I think we do that up above a bit. And then we can also check how good the linear model was. This stands for linear model. And we have a y-intercept, so to speak, and a coefficient for hours of sleep, and a coefficient for calories burned. And here we can see that this has more effect on predicting mood than this does. That's what the coefficients mean in regression, at least in this case. So hours of sleep is a little bit more has a little bit more effect in terms of people's mood than calories burned, but that really depends on the units that are used. So it's hard to say that exactly, actually. So anyway, we get some data that we could learn how to read about the regression, and we get a measure of the error here. This is another measure of the error. Both of these are commonly used error measures. Anyway, so now we go back and we're going to do our neural network. And here we have set the size, the dimensions of the network. But as I recall, I think we could change these. So we could make a more complicated neural network. We could have more nodes here in particular if we wanted to. And perhaps that would give us a better prediction, a better model for the data. So here we set out by initializing the weights randomly, just like we did before. We define our normalizing function. We read in the data. We can look at the column names for this data, but we're not going to use all of them. So we're going to just select the mood, calories burned, and hours of sleep. So mood is the thing that we're trying to predict. So we didn't actually use, I said that those dots had different colors, and they were actually one of these other variables. I think it was active, whether the person was considered active or not. So one of the colors represented active and the other color represented non-active, but we're not using that in the neural network. So we're only using two input variables, calories burned and hours of sleep. And then we split in training and testing here, training and testing. And then we have a function that we've defined up above called full update weights, or actually maybe we're defining it here. Hopefully we defined it above as well. Define a function to loop through every row of the data set. So we're going to go for every row in the set of row names. So now we run that full update weights repeatedly, and we're going to check the error on the test set. So we're going to see how the test set does with our model or our network. We're going to train our model with the training set and test it with the testing set. So we're running the full updates each time using the training set. So if you go back up several lines up above in the code, you'll see that we're currently working with the training set data, and we're using that to update the weights. So we run the full update weights on using the training data, and the weights get updated. And then we run it again, and the weights get updated again. And then we run it again. And each time, by the way, we have to, after we run full update weights, then we have to take, then we set the results into here, and then we have to use those to update the weights, W1 and W2. Then we run it again with W1 and W2, and so we update the weights again. And we also can check the cost, but the cost is not so interesting right now. But it's not so interesting because we're doing it on the training set. So of course we expect the cost to go down on the training set. But we can still check. And here we see that the cost is currently here. Then we do it again. The cost has gone down on the training set. Not so astonishing, but that's what's happening. Then we run it again. We see that the cost still continues to go down. It doesn't have to go down, but you would expect that it would. And then we want to run it on the test set finally. So we run it on the test set, and it does quite well, actually, even better than might be expected. Finally, we're going to we're going to not do this manually. Each time, update the weights once by running this, and then do it again by running this, and then doing it again. But we will run that through a loop so that we can set the number of times we want to run this. We can run it 50 times or 100 times or 500 times. The standard is usually to do it something like 500 times, but there's no particular correct number of times to do it. But anyway, we can run it through a loop. So we can run the update weights function through a loop. And we'll call it, that whole process, we'll call that this. And as we go through epoch 1, epoch 2, epoch 3, we can also print out the error. And we can see that as we go through the epochs, the error does seem to be decreasing. Now, again, that doesn't have to happen, but it is happening. And of course, it is what we want to happen. Okay, let's talk a little bit about what are called the hyperparameters. So in our coding so far, we have the learning rate, and we're using the set seed, and that can actually be considered, typically that's not considered a hyperparameter. It's just a way to produce reproducible results so that somebody else who's running your code will get the exact same results as you, even though they're using the random number generators. But we can also think of it as a hyperparameter, and you'll see what I mean in a minute. Also the number of nodes and layers and the epochs. So let's just read through this. By experimentation, we'll see that learning rates, set seed, and epochs all have large roles in improving the performance of the net. Now, of course, the learning rate will have some role in whether you're finding a lower point. So normally you think that the larger the learning rate, the faster you would get to a low point in the cost curve. But if we also said that if the learning rate is too large, you might sort of overshoot the low point of the cost curve. So we have to sort of play around with different learning rates and see which one will give us the best network. In other words, gives us the best predictions with the lowest error, and then we have a good neural network. And so you might just have to play around with different learning rates. You might have a loop that goes through many different learning rates and then chooses the one that gives you the best overall result. Of course, that's going to take a lot of computing power. The same thing with set seed. So what role does that have? Well, we saw that in this picture, if our initial weight was, say, at B, maybe we'll only get to here, and we'll never get over up here and find this low point. So what can you do? The initial weight, the randomly initialized weight, was here. So what you could do is set seed in try different set seeds, and that will basically say, well, maybe sometimes your random weight will be here, but maybe it'll be here some other time. Maybe it'll be here some other time. Maybe it'll be here some other time. But maybe it'll be here some other time, and maybe it will be here some other time. So in some of these, you might actually get to this low point or get close to this low point. So by choosing many different initial randomized weight settings, you could possibly find a lower value on the cost curve. So that's another strategy for improving the performance by checking different initial randomized settings. So we can say that one explanation for this is that there are many local traps to get caught in. That is, many local but not absolute minimums of the cost function to get stuck in. Changing the set seed changes the original random settings for the weights. The effect of this is to start us out at a different location on the cost curve. We say surface, not curve, because we have multiple dimensions. In fact, we could say hypersurface. From there, we may discover a particularly low cost point, or we may get stuck in a not so low, but still local minimum. As was suggested earlier in the text, we may liken this to the genetics that a child is born with. Given a particular starting point, may have a significant effect on your future accomplishments. And now we say we've created a neural network with 3 layers. In the next chapter, we will use classes to make our code more elegant.